So, good morning, afternoon, or evening, everyone, wherever you are to join our session on the frontiers of climate research. My name is Philip Stier, and I'm a professor of atmospheric physics in the Department of Physics. We also serve as head of atmospheric, oceanic, and planetary physics, which is one of the sub-departments of physics in which we strive to advance our understanding of climate of planet Earth and many other planets. And with me tonight are my two colleagues, Hannah Christensen and Myles.
Hi, everyone. Great to see you.
Hello, everybody. Nice to see you all.
Great. So our session today is on the frontiers of climate change, from fundamental physics to digital twin Earths. And I'll start off by provide some brief motivation, really, before handing over to Myles and Hannah as the main speakers, followed by a discussion at the end. You can put your questions anytime during the session into the Q&A box of the attendee hub, and we will take questions in the end and hope to answer all of your questions. So coming to the main topic of the session, on fundamental physics, or from fundamental physics to digital twin Earths. So you're here, so it won't be a big surprise to you that climate change is one of the greatest challenges facing society. And we know this because we know the Earth's temperature is rising. And these are just the latest observations of the temperature anomaly of the global mean temperature of the Earth, as you can see from pre-industrial times to present day. And in particular, you'll be aware of this strong increase in temperatures since the 1980s till present day, almost a whole degree Celsius of an increase in global mean temperature. We also know why, because we can attribute this increase in temperature change, increasing temperatures, to increasing concentration of greenhouse gases. And on the left-hand side here, you see the atmospheric concentrations of CO2 as measured on a laboratory in Hawaii. And you see this corresponds fairly nicely to the increase in the temperature. And obviously, we can attribute this in much more detail than just comparing two figures. So climate physics has delivered the scientific evidence to attribute global warming to anthropogenic greenhouse gases. And by now, it's probably fair to say this is widely accepted and almost globally accepted. So this has led then also to the Paris Agreement in 2015, in which nations of the world really agreed to hold the increase in global average temperatures to well below 2 degrees. And to pursue the limits to even be lower, to only 1.5 degrees, and recognizing that this is reducing the risk of climate change. And as you remember from the first slide already, we're currently already at 1 degree, roughly. And if we have the ambition to go to 1.5 degree, this is a very ambitious goal. But you can ask yourself, has climate science now completed its objectives? Are we done? Have we told policymakers everything they need to know? And the answer to this has to be no. So there are many open questions in climate research, and they're here summarized by the current grand challenges in the World Climate Research Program, comprising many of these. And you see they touch many parts of the climate system, from clouds and ice, sea levels, all the way to carbon feedbacks and predictability of climate, and many fundamental questions in each of these topics. Just want to point out that Oxford covers really all of these research questions from end to end. And if you want to learn more about this, you can go on the Oxford Climate Research Network webpage, and you can find much more information about this. But I just want to make the point clear why these challenges remain. And this is simply the fact that also scientific uncertainties remain fairly high. And these uncertainties translate into uncertainties of the climate sensitivity. So how warm will it actually get if we know the perturbation? The regional impacts of climate change. So how will it affect us regionally and locally where people live? But then also the mitigation options. What do we need to do to avoid this? And at the heart of these questions are still fundamental climate science research questions. I just want to illustrate this point on one example here and just show you a few nice pictures of the Earth and to flag up some of these questions and why they are so important still. So this is the Earth as seen from space, from polar orbiting satellites. So you see there's some gaps between these overpasses of the satellites. So these are very low flying satellites to observe the Earth in great detail. That's why you get these striped bands of the Earth. And what you see from the distance is that the Earth appears fairly white because clouds reflect a lot of sunlight back to space, and that makes these clouds appear very bright. And you also notice, particularly over the oceans, that the Earth is much, much brighter than the underlying ocean surface here. So that means when there's a cloud, they reflect much more sunlight back to space than the ocean otherwise would do. And therefore, these clouds generally tend to have a cooling effect, at least the low-level clouds. But this picture from a distance hides a lot of the beauty and complexity that you want to have to understand to address some of these questions. And so let's look a little bit closer and just focusing on this area here in the Southeast Atlantic. And you see when you look closer at these clouds, you see a very, very complex structures across many, many different scales. And we can look closer still, and you see again, you reveal more insights and complexity here. But we can look closer and closer, and you will still discover new and interesting features in these cloud decks. To the point when you reach almost a satellite resolution here, and just to give you a point of scale, some of these small cloud features here and sort of the kilometer and 100-meter scale, the bigger ones here maybe tens of kilometers. And you also see that within these cloud decks, there are areas that are very bright, and so they reflect a lot of sunlight back to space, and they often break up into these open areas that are very, very dark. And they would obviously be not as cooling as a bright cloud deck. So we really need to understand these questions. And there's one more zoom in. The problem for climate research, or a big problem for current climate research, is that clouds are too small to be represented well in current global climate models. And they drive a large part of the current climate model uncertainty. And it's just the only technical slide I have. It won't be too much detail, so just let's focus on a few simple points from this slide. So you see here the previous generation of climate models from, say, 5 years ago, and in blue. And in orange, you see the current generation of climate models as they're just being evaluated and being assessed. And on the left-hand plot, you see so each climate model is a little circle here. And then on the left-hand side, you see basically the spread among climate models from the previous generation to the current generation. And what's shown here is what's called the equilibrium climate sensitivity. That gives you an idea how warm it will get in response to a known perturbation. And what is interesting really that in the last decade or the last 5 years really here, instead of reducing the uncertainty further among these climate models, we have actually increased the spread of climate model responses. So it can get either very warm or much less warm among these different climate models. And when you look at this in detail, and I just put the slide up on the right-hand side, we can trace this back in these climate models primarily to what's called cloud feedbacks. And this is the response of clouds to a warming world. And we now understand that if you, for example, had less low-level clouds, as we've looked at here, then you would reflect less sunlight back to space, and it would accelerate warming. So what are we going to do about it? Just a couple of examples of ongoing research that's from my own group. Well, we want to understand, for example, the breakup of these cloud decks here from satellite data. The problem is there's a huge amount of satellite data, so it's very hard to handle this manually anymore. So we use new techniques from machine learning and data science in which we go through the entire satellite records, 20 years of satellite imagery, to find these transition areas where these cloud decks break up into these pockets of open cells, that's what we call them. And this allows us to do a first global analysis of something we couldn't count by hand anymore because there's just too much data there. Or sometimes you really want to get into it and measure the detail, and just on the right-hand side here, measurements taken in the same area as a satellite image here. And it's again, this is a measurement from an aircraft measurement campaign with NASA and the UK research aircrafts together, where you really fly into these clouds and analyze the cloud and the atmospheric composition in great detail. And these are just some of these examples from the observation side, because we will talk a bit more about models in a minute that showcase how much work is still being done and needs doing to understand, for example, here the role of cloud feedbacks and the role for climate change. But now I want to move on to really the main events of this evening and introduce the first speaker. So the first main speaker today is Myles Allen, who's recently been described by the BBC as sort of the physicist behind net zero, and you'll understand that in a minute. But he's been working on climate change and anthropogenic perturbations to the climate system since now the early 90s. He's been awarded quite a few prizes. I won't list all and embarrass him further, including the Appleton Medal and Prize from the Institute of Physics. But he was also the first one who proposed the concept of the global carbon budget, where you could show that the peak warming that the Earth experiences is really determined by the total amount of carbon dioxide we released into the atmosphere, not the emission at any given time. So Myles is a professor of geosystem science in the Department of Physics and the Environmental Change Institute of the School of Geography. He's also a fellow of Linacre College and importantly, a director of the new Oxford Net Zero initiative. And today he will be speaking about the main theme of this event, from fundamental physics to digital twin Earths. Over to you, Myles.
Well, thank you very much indeed, Philip. And thank you for that introduction. Very nice to meet you all. Good morning, good afternoon, good evening. I just wanted to share some thoughts on this challenge. Particularly, I mean, Philip and I were chatting about this before this session, and the sort of basic question that Philip raised, and addressing the question that, you know, there is a bit of a danger, I think, that often when I speak to school strikers, I've been spending quite a bit of time over the past few years talking to young people who are very passionate and enthusiastic about climate change and doing something about it. And you know, very often they ask me, but when they discover I'm a university professor, they say, "Oh, what subject should I apply for if I want to sort of make my mark in climate at university? You know, should it be politics, or should it be you know, environmental science, or engineering or something?" And I reply, "Well, if you can do it, physics or maths." And they often seem slightly puzzled by this reaction, because I think there is a perception out there, at least, as Philip said, by many people, that the science is kind of done. We know what's happening, and now it's just about getting on with addressing the problem. And that's really what this session is all about. There are some things that we do know what's happening, and I'll sort of start with that. But it is because actually one of the other things I'm doing when I'm not talking to school strikers is spending an awful lot of my time trying to explain to people that climate change is actually not perhaps as complicated as they thought, and in order that the people can't sort of shelter behind the complexity to avoid actually thinking about the hard choices they have to make in addressing it. So I'm going to kick off with a few slides, because I have them here just to sort of give you something to look at while I'm talking. Let's go sharing the screen. If I'm talking about this this challenge from going from fundamental physics to the concept of a digital twin Earth, Hannah will be taking you much further in terms of the sort of state-of-the-art climate physics that we're working on at the moment. This is more the lead in, the warm-up act, so to speak, to talk about why we need it, or one very specific application of why we need to understand the fundamental physics of what's going on in order to make sense of climate change as it's happening at the moment. Philip mentioned I direct the new Oxford Net Zero initiative. This is an initiative funded by the university itself, stepping up to draw together and also augment and build up our research effort in the area of net zero, primarily focused on the challenge of how we get there, what net zero means, but also how we achieve it, how we can manage to, as a world as a whole, end our contribution to global warming. The sort of first question we need to ask is is this one. You know, I mean, we're talking about digital twin Earths, these sort of these models that can only be run on supercomputers that require a small nuclear reactor to power the supercomputer. Do we still need them to predict global warming? And since it's a physics meeting of minds, I have to show you an equation. I'm sorry about that. It's not an option. This is a very important equation, but it's not an equation you see very often. But you should see it more often because it's basically the equation that determines global warming. And it's just to sort of take you through it. The warming you get over a time interval that's relevant to anybody's lifetime, so a few years to a few decades, is comprised to a remarkably high degree of precision by the sum of just three quantities in descending order of importance, if you like. The first, this E bar delta T quantity, is the average rate of emissions of carbon dioxide multiplied by the time interval, which of course is just the cumulative sum, the integral of the carbon dioxide emissions that we dump into the atmosphere over that time interval. So that explains 80% or so of the warming we've seen so far. It also explains a similar fraction of the variation between different scenarios in the warming we might experience over the 21st century in the future. And the further we go into the future, the more the warming is just about the carbon dioxide. And the reason for that is very simple. Carbon dioxide is a cumulative climate pollutant. The more carbon dioxide we dump in the atmosphere, the higher the temperatures go. And there is this very simple, roughly 0.4 to 0.5 degrees per trillion tons of carbon dioxide relationship between the global temperatures and the carbon dioxide we release. So that first term is really the simplest one, and we've understood that for a decade or so now, and we've been kind of quibbling ever since with what do we do about everything else, and that actually boils down to two pretty simple terms as well. And I've spent an awful lot of my life over the past couple of years really trying to work out how can we follow Einstein's dictum and make this as simple as possible, but not simpler. And I think this is about the limit of how simple we can make it. There's the change in global energy imbalance that we see. By the way, can somebody tell me in the chat, can you see my cursor or not on the well, I'll assume you can't, so I'll just wave my hands and describe things. So if you right in the middle of the screen, there's a delta F over alpha term, which is the change in the global energy imbalance over a few decades that results from other stuff, not carbon dioxide, but things like methane emissions or changing aerosol pollution. And those aerosols generated by the sulfur emissions from power stations and the like, those interact with the clouds that Philip was showing you and actually have a cooling impact on the global climate. So that they're quite an important driver. Again, this is sort of at the 20% or so level compared to the carbon dioxide signal on the left. And that's and so that's the middle term here. And then the right one, the right term, the third one, is the smallest, and I've often sort of felt I'd quite like to get rid of it because basically three terms in an equation, well, any equation at all, you lose about 80% of your politicians. An equation with more than one term in it, you lose most of the remainder. So an equation with three terms is quite sort of exclusive. But we do need all three terms to sort of accurately convey what's going on, because if we were to reduce carbon dioxide emissions to net zero, which is what we're aiming to do to stop carbon dioxide causing global warming, and if we were to stabilize the forcing due to the global energy imbalance, due to other climate agents, due to methane and aerosols and so forth, we would still get a little bit of warming in response to past increases in non-CO2 forcing. So that's accounted for by this third term. That row is it's quite a small number. So again, that's contributing at the few percent level. But it's sort of needed there because otherwise you might give people the impression that if we manage to stabilize the global energy imbalance and get due to other stuff and get CO2 emissions to net zero, we would stop the warming entirely, and that's not over many decades. That's not what would happen. These three terms, if you put them together, actually explain, as this lower panel, which is one of the illustrations from the recent Intergovernmental Panel on Climate Change special report on 1.5 degrees, they pretty much explain the warming that's happened over the 20th century, and they explain differences between different scenarios for the 21st century. So, it's on this level, you'd think, well, with one equation with three terms in it, three undetermined coefficients, we kind of know what the values of these coefficients are from what we've observed so far about climate change to date. For predicting global average temperature, it sort of almost looks like we're done. But, and there's of course a very important but here, what this actually is more a statement of hope. We're hoping that this explains everything. The reason I'm saying we're hoping this explains it, or we're hoping therefore that this equation is enough and that we don't need to resort to supercomputers to predict global warming, which may seem so actually no, I should have let's hope. Sorry, I've got this wrong, actually. I've got the joke wrong. Damn it. What it should say, let's hope so. I beg your pardon. What I mean is that if this equation, if we manage to stop emissions, if we manage to stop the warming relatively soon, and if nothing particularly surprising happens as the climate evolves in the future, then this equation works, and it actually describes the future development of global temperatures quite accurately. But the challenges we have are, if we, on the one hand, if we don't manage to reduce emissions, if we actually allow climate warming to continue up to the sort of 3 or 4 degree levels, that's when this little simple equation starts to break down. And that's when you really would need a supercomputer to predict actually what's going to happen, even at the global average temperature level, because we can no longer assume that the three coefficients that I've got in this little equation in front of you will remain constant. We can't assume that behavior which we've seen already will persist into the future. And so that's one reason I'd say let's hope that we let's hope we do that we don't need supercomputers to predict that breakdown. And the other aspect of why I think so there's on the one hand we hope that we will manage to get the problem under control before we sort of reach those global non-linearities that would require a supercomputer to model them. And the other side of it is, we hope those global non-linearities are not actually just around the corner, but of course we can't be sure of that. One interesting aspect of climate change at the moment is that the climate is actually changing right now faster, it's warming faster than it has ever warmed in history. Even though there's all this ambitious commitments being made about reducing emissions, what's actually going on at the moment is we are sort of perhaps getting carbon dioxide emissions sort of more or less under control, but we're not reducing them yet. But other drivers of climate change, notably methane and aerosols, are actually driving warming towards faster than ever, driving temperatures up faster than ever. So this is a situation where we are at the moment entering a decade where the world is going to be warming. On our best estimate predictions at the moment, human-induced warming is likely to be at its fastest rate ever, and surprises may happen. And it's if you're moving into uncharted territory, you need fundamental physics and detailed simulation to understand to understand the response and to predict with any confidence what's going to happen, and more particularly what's not going to happen. So there is a concern that as we sort of stress the system through into ever more extreme under ever more extreme pressure, that we will need ever more detailed understanding of the physics driving it in order to predict the response. But so that's apologies for getting my punchline joke wrong on the slides. But so that was what I wanted to sort of the tension we have when we're talking at the global average temperature level between wanting to make it clear to people how simple the problem is on the one hand, but also to make people realize that it's possible we will need to understand the detailed complexity in the future on the other. Where I can say with absolute confidence that we do need the detailed understanding encapsulated in these digital twin Earths is when we're talking about what I would regard at the moment, and this is where I'm just expressing my own views, but it's a personal opinion. Hopefully, we'll be able to argue about it in the chat. There's actually something even more important than predicting global warming at the moment, and that is understanding events like this. And I'm sure that listeners in North America will remember this. This was that horrendous cold spell that you had going all the way down to Texas in the US earlier this year, and which immediately triggers arguments about whether this kind of event is being made more likely by human influence on climate. You can see that the headlines immediately started appearing about as soon as this extreme event happens, with how scientists were arguing about whether or not the warming Arctic, driven by human influence on climate, was to some extent to blame for snowstorms in Texas. And I'm going to sort of digress briefly here to talk about how we can use our fundamental understanding of chaotic systems, of fundamental physics, to understand how you could have a situation where a warming world actually triggers a colder event. So suppose we've got this is of course the classic Lorentz nonlinear model of the atmosphere dating back to the 1960s, three coupled ordinary differential equations that display this incredibly rich chaotic behavior. And I'm just going to introduce a variant on it, which was suggested by our colleague Tim Palmer back in the 90s, I think, or early 2000s, where you can imagine the Lorentz butterfly, sort of going around this, imagine blowing on the butterfly from one side. What does it do to the density of points in the butterfly? And so in Tim's little variation, he introduced a wind blowing on the butterfly, blowing on the Lorentz attractor in the direction of the arrow shown by the black arrow you can see on your screen now, and look at what happens to the points on the butterfly. They carries on orbiting around the attractor as it did before, but you'll notice that there's many more red points down the red is the sort of perturbed attractor, and there's many more red points down in the lower left than there are in the upper right. So although the forcing is pushing towards the right of your screen, so as it were towards higher temperatures, it's actually having the effect of shifting this nonlinear system, the center of gravity of the nonlinear system, towards the left. So it's possible in a nonlinear system for the system to move in a direction that's actually orthogonal, or even beyond orthogonal, to the forcing itself. And as a result, we see in this system, the impact of the forcing is to make very high, very warm events, so to speak, less likely, even though the actual impact of the forcing on those events themselves is to make them warmer. So you can see here, the green lines show without the forcing, and the red lines show trajectories with the forcing. And you'll see the red lines are displaced slightly. If I zoom in, you'll see the red lines are displaced slightly to the right of the green lines. So we are seeing here the forcing making individual events warmer, so to speak, but making the prevalence of cold events down off on the left, over to the left, more frequent. So understanding how the probability of different events are changing requires a fundamental understanding of the underlying physics of what drives extreme weather events. One of those challenges, that grand challenge, WCRP grand challenges that Philip highlighted, and this is one of the areas which Oxford has actually really pioneered over the past few years, and which remain a high, one of our priorities for research, because this does matter. Because one thing I just draw your attention to here, the reason you get this sort of somewhat counterintuitive behavior is because in the Lorentz system, the system is acutely sensitive to external drivers when it's in this region here, when it's around the body of the butterfly, so to speak, the point where the two wings join. That's where it's sensitive to an external driving. Once it's out on the wing of the butterfly, it'll carry on around that wing. That's the way this system works. So it's the response down in the heart of the attractor, so it's the response to, for example, in a completely different part of the world, the response to climate change may then have a knock-on effect at a remote region, and that's why we can see these complex relationships between the overall climate driver and extreme weather events. Just to wrap up, I'm just going to illustrate this, why this sort of stuff. I mean, I wrote a paper back in the early 2000s talking about this way of, could you blame anybody for an extreme weather event? And it was to motivate the paper. I asked the sort of rather whimsical question, do you think it would ever be possible to sue anyone for changing the climate? And interestingly, this is starting to get really quite topical. And I'll just wrap up with another recent study that we published in Nature Geoscience just a few weeks ago, looking at an example of a potential extreme event, the changing risks of a outburst flood, a glacial lake outburst flood in Peru, which and there is actually, and the reason it's topical and relevant to that rather whimsical article I wrote back in 2003 is the residents, or some of the residents of the city of Juarez, which is threatened by this glacial lake outburst flood, are actually taking a German power company to court to contribute to the costs of stabilizing the lake. So let me just take you through what this sequence of pictures shows us. Back in 1939, this was a very large lake trapped behind glacial moraine here. You can see there's the lake behind the glacial moraine in 1940. Then there was a huge and devastating flood in 1941, which killed almost 2,000 people as the lake burst out past the moraine and down the valley to a quite densely populated city below. And you can see even in 1970, the lake was just a remnant of its previous self. You can kind of see the outline of where it had been and that small sort of turquoise patch in the middle, but it's growing. And you can see that as we get closer and closer to the present, the lake is getting bigger. And the citizens of Juarez are already getting nervous about what, they basically recognize they're going to have to intervene very expensively to try and stabilize this. And the crucial point, the point of this paper, is that global warming is clearly playing a role in destabilizing these glacial moraine lakes. And so the citizens of Juarez argue they have a case against those companies that are responsible for the emissions. This is showing the modeling we were doing about how the glacier is retreating dramatically to drive these glacial lake outburst floods. So, it's no longer enough just to say, as Bloomberg Businessweek said after Hurricane Sandy, it's global warming, stupid, that's enough, go and shut people up that way. We need to do the science to establish what global warming is actually doing, because as I frequently point out to people, if we're asking people to do something about climate change, they deserve to know what climate change is doing to them. And that is at the heart of a lot of the science we're doing at the moment in atmospheric, oceanic, and planetary physics. Back to you, Philip.
Fantastic, Myles. Thank you very much. Just to remind everyone, we will take questions at the end of this session, and I'll invite already Hannah to share her screen while I introduce her. So you can continue to put your questions in the chat, and we take them at the end of this session. But a fascinating talk, Myles. Thank you very much already. So while Hannah's setting up, and she's already ready, so I just want to briefly introduce her. So Hannah is a climate physicist, and she focuses on fast atmospheric processes, things like thunderstorms, clouds, turbulence, but as well as large-scale climate dynamics. And she cleverly combines theory, models, and observations, and particularly increasingly the use of these ultra-high resolution climate models that we will hear about, as well as machine learning to answer climate science questions in this area. So Hannah is an associate professor of physical climate in the physics department, our most recent faculty appointment in climate physics, but she's also a David Richards Fellow at Wadham College. And today, Hannah will speak about the future of climate prediction, digital twin Earths. Over to you, Hannah.
Great. Thank you very much, Philip. And thank you to everyone who's turned out to hear our presentations today. Great. So I'm really going to pick up where Myles has left off, particularly telling you a little bit more about what is this thing that we're hearing about, digital twin Earths. So firstly, I'd like to just take a step back and set the scene. And so what is the problem that we're interested in? Well, we have this very beautiful, intricate, complicated Earth system. We want to predict what's going to happen over the next few days, weeks, months, all the way out to decades and centuries. So this is the problem. Particularly, we want to ask questions about how we are influencing the way that the system is going to evolve in time. And also questions about what we do, what changes can we make today, which are going to influence, this impact that we're having, and how we should best make these changes to have the kind of biggest impact on the future evolution of the climate system. So this is the problem, and what's the solution? How can we actually answer these questions? And the solution that we've come up with is to build computer simulators of the Earth system. So the idea is that we know the equations of physics which describe the Earth system. So for example, we know the Navier-Stokes equations, which tell us about momentum conservation in the atmosphere and oceans, as well as many other equations. And we can encode these then into a computer model, which is what I'm showing schematically on the right here. So kind of a key point that I want to communicate here is that when we put these equations into a computer simulator, we have to define a particular resolution. So this is effectively a kind of degree of pixelation of our model. So within each of these little squares, these pixels, we're modeling the atmospheric state and the ocean state, and etc. as being a constant. So we're representing the atmosphere within that pixel as having a kind of constant wind speed, temperature, water vapor content, and so on. And we have this as a function of height and then as a function of position on the Earth. But of course, there's a lot of processes, important processes going on at smaller scales than this pixel scale. And these are not going to be explicitly captured in our model, but we have to represent them in some way. And so we do this through very sophisticated approximations, but they are approximations nonetheless. And so this includes things like clouds, which Philip referred to earlier, but also convective thunderstorms, kind of turbulence, or things like this. So to really just hammer home this problem of the kind of pixelation of our models, I'm showing you here 3 examples of model resolutions and how they've evolved over time. So the top panel here is showing a kind of typical resolution of models that we were using in the mid-90s. So these were models that went into some of our earlier IPCC assessment reports. And here the pixel size is 250 kilometers on a side. We're now moving through the mid-2000s, so we've increased to 120 kilometers. And here at the bottom, I'm showing the kind of resolution of really a state-of-the-art climate model that is going into our latest assessment report, which is due to be published this year. And in that assessment report, actually, we have kind of two different kind of classes of models. And this is then actually some of the higher resolution models that have gone into this report. So really a 60-kilometer resolution, quite a fine resolution. But you can see that, I mean, even 60 kilometers is not really fine enough to capture a lot of these small scale features. And so we do have to make approximations. And these, I mean, the choices that we make when making these approximations, particularly convective thunderstorms, can actually have very large impacts in our models. So a nice way to see this actually is to take a model like this that we would run for climate and look at how it behaves on a much shorter timescale. So let's make a weather forecast with this model. So here we're tasking our model, our climate model, with predicting Hurricane Sandy, just on a very short timescale of 5 days. And what we've got here is the same model, but we've swapped out the convective thunderstorm representation and put in a different representation of storms, but one which is kind of equally likely. So a priori, we wouldn't know which one was going to do better. And when we run then kind of forecast for Hurricane Sandy, so here we're showing the track of the hurricanes for the two different kinds of model. It's pretty clear that the red model is doing a lot better than the blue model. So the blue model is really even, quite close to the time that the hurricane made landfall in over here in kind of New York area. We can see that it's getting the track completely wrong. And so I think that the point I want to make here is that, you know, even these kind of 60-kilometer scale high resolution models that we're using today, you know, struggle when it comes to representing things like extreme weather. And it's really coming down to some of the approximations that we're making, that we're forced to make, particularly to do with clouds and convection. So what can we do then? What's the possible solution? Well, let's just move to a much higher resolution model. So here I'm showing images taken from a series of what we would call global storm resolving models. So we're now able to run our models at a very high resolution of only a couple of kilometers. And so these figures are taken from a very recent intercomparison, the first intercomparison of this kind of model. And the question is, can you see which of these images is the satellite data and which are the models? So I'll give you a couple of minutes to look at that before I tell you the answer. And I mean, the take-home message here is that they do look really excellent. And this is what we mean by a digital twin Earth. So it's a very high resolution computer simulator. And moreover, we blend this model with the most up-to-date observational data that we have to really pin it very closely to the current state of the atmosphere. And this then provides us effectively with a kind of digital laboratory in which we can perform experiments. And these can then be very detailed experiments. You know, what happens if we plant a forest here or we cut emissions here, as well as asking questions to do with kind of fundamental atmospheric physics. So for example, you know, trying to understand why clouds form the kind of myriad of structures that they do, as Philip pointed out. And this one in the middle here, this is the satellite image. Okay, so on the previous slide, I was definitely saying how wonderful these digital twin Earths are, but how great are they really? And so what I'm showing here is a zoom in of the satellite image, that one in the middle, and just two of the models. And so here in these zoomed in images, you can see a bit more of the features of these models. And the two models I've chosen here, this one called NICAM and ICON. I've chosen these because they're actually quite similar in the way in which they were set up, and because they're also both coming from modeling groups which have a lot of experience with running these very high resolution models. So they should perform very similarly and both very well. But what's very clear from these images is that actually they look very different to each other, and they both look pretty different to the satellite data as well. So I mean, if we take NICAM, for example, the clouds seem to be a lot rounder, kind of a lot more patchy, blobby, and much less smooth than the kind of satellite image that we're seeing here. So the thing to remember when we're working with these digital twins is that the models are not the same as the real world. So before we can launch into doing our experiments with them, we need to have a really good idea of what they can and cannot do well. So really, we're looking to kind of quantify the differences and the similarities between the models and observations. So, okay, so let's start off thinking about how we could do that. So why not start off actually with saying, how can we quantify the visual similarities and differences that we're seeing here in these cloud fields? I mean, can we go further than just eyeballing these images and saying, oh, NICAM looks a bit blobby compared to the satellite? Do we have a framework for doing this? And the answer is yes. An ideal mathematical framework for thinking about this is the mathematics of fractals. And so fractals are mathematical objects which have a kind of nested repeating structure on all scales. So I'll try to explain what I mean by this. So if we take the fractal in the middle here, the Sierpinski triangle, what you can see is if you allow your eye to focus on a smaller region of the fractal, so for example, this triangle in here, and then you zoom out and look at the bigger picture, you'll see that the two look the same. So this is what we mean by having this kind of nested repeating structure, this kind of self-similarity. And the same is the true of these other two fractals. Perhaps some of you in the audience will recognize this one on the left. This is a very nice sculpture which is in the grounds of Magdalen. So next time you're in Oxford, you should come and have a look at this sculpture. Great. So what else am I showing here? I'm showing at the bottom here this thing called the fractal dimension, D. And so what this tells you is it kind of characterizes the nature of the fractal. So for example, where a 1D object would have a dimension 1 and a 2D plane would have a dimension of 2, fractals also have a dimension. So the higher the number, the kind of more crinkly the fractal, the more it's filling out space. And we can see that this the triangle here in the middle does look a bit more like a 2D plane than the Cox snowflake on the left. So we can use this dimension to characterize the fractals. And clouds are also fractals. And this is something that has been recognized about clouds pretty much since fractals were identified by Mandelbrot as an interesting concept. And just to demonstrate this, I'm showing an image of a cloud field on the left and a zoomed in image of the cloud field on the right. And if I hadn't told you which one was which, you really wouldn't have any particular sense of scale of how to tell which one was the zoomed in and which one was the zoomed out. And if we zoom, we could imagine zooming in again on this image, you would again see these kind of multi-scale structures appearing. And so we know that clouds in the real world are fractals. So the question then is, well, do these ultra high resolution digital twin Earths, can they reproduce this behavior? And so this is a question which my master's student, Oliver Driver, has been working on this past year. And extraordinarily, the answer is yes. These ultra high resolution models do indeed show fractal cloud behavior. So you can show this. I'm showing some figures from Oliver here. So what he's plotted here is he's gone through and identified cloud features in these images. So these are clouds of a particular kind of height, so particular depth. And he's measured the perimeter of each cloud and the area. And if we have a straight line relationship between these two measurements, this demonstrates self-similarity. And this actually indicates then that we are seeing fractals. And the gradient of the line of best fit then tells us the fractal dimension. And we can see that the satellite data coming from this Himawari satellite on the left is showing nice fractal behavior, but really extraordinarily that the icon model is also showing this behavior on the right. And I want to really emphasize how exciting this is. I mean, this is an emergent property coming out of our models. This is not something at all that we would be able to kind of go in and hard code or tweak in our models. It's really indicating that the model is able to kind of aggregate self-organized clouds in a way which is realistic compared to observations. And so really this is telling us that it's getting some aspects of the kind of fundamental physics of the atmosphere really spot on in these models. So what Oliver's done then is to kind of summarize this behavior. He's gone ahead and calculated the fractal dimension of all of these different models that we looked at here, as well as a few more that have been run as part of this into comparison. And we can see here's the icon model we just saw on the previous slide, and that does perform really well compared to the satellites. But actually this fractal dimension turns out to be a really nice way of, quantitatively comparing the different models. So this other model we looked at earlier, it comes out that it has a much smoother fractal dimension, which is what we could kind of see in the cloud fields. So this is a nice way then of kind of quantifying this visual similarity and getting at which of the models are doing better than others, which is an important first step, and then in working out which ones might be more trustworthy for asking certain questions with. And so why does this all matter? Why should you care about kind of fractal clouds in models? Well, I think something that Myles alluded to. So, when it comes to how our climate is changing, one of the big things that we really care about is how extreme weather events are likely to change in the future. Sorry. What I'm showing here is actually a particular kind of extreme weather, which is coming about because of the organization of convection into large features, such as this is a mesoscale convective system here that's forming over Kansas. And again, we're seeing it as such a big organized system here in the middle. And the reason these are really important is because they often lead to very extreme rainfall, flash flooding, strong winds. These are all things which are very high impact and felt by us on the ground. And our current generation climate models, like those in the IPCC reports, have really struggled to represent these kind of organized convective systems. So how can we expect those models to give us good statistics as to how these kind of extreme weather events will change in the future? But with this new generation of ultra high resolution digital twin Earths, we can actually start asking questions about how extreme weather like this might change. And so this then really brings me to a kind of summary slide. What's the kind of road ahead as I see it here? These new digital twins are really exciting, but we shouldn't get carried away. We need to start off by very critically looking at them and trying to compare them to the real world to see what they can do well in order to know what kind of questions we can ask using them. It seems like this is a great time to bring together the weather and climate communities. So, firstly, both of the talks you've heard today have stressed how we're really interested in how these kind of extreme weather events are changing in the future. But also, if you think back to the example of Sandy that I gave earlier, by running our climate models in a more initialized way, so producing kind of weather type forecasts with them, this is a really good way of discerning whether our models are able to do a good job. I couldn't give this talk without mentioning machine learning, really. These ultra high resolution models produce vast quantities of data. So this diamond into comparison, they only ran the models for 40 days, and they were very selective in what fields they archived, very selective. And yet each model kind of data that they stored accounts for more than 50 terabytes of data. So there's a huge amount of data that we need to work with. And really the key question here is working out, the key here is working out what the important questions are, kind of how to frame the questions to learn something about the physics. And then finally, we need to be equipping the next generation, our wonderful undergraduate and postgraduate students to be able to address these problems. So not only training them in kind of suitable statistics, big data techniques, but we do really need to be training them in kind of fundamental physics to enable them to ask the right questions when looking at these kind of simulations. So that's it from me. Thank you very much.
Fantastic, Hannah. Thank you very much for this. And I'm inviting now Hannah and Myles to come both back on screen so that we can start with the question and answer session. I'll start off with one question by John Twiddell to Myles, and this is about the units of his equation and if they're consistent. And Myles, this should be answered.
Absolutely, I love the fact that John was on the checking my dimensions, but yes, and it gives me a chance actually to talk to several of the other questions as well about that simple equation. So we've got this average emissions over a time interval. So that's tons per year times, that's just tons of CO2. That's watts per square meter, but then we're dividing it by this coefficient, which has dimensions watts per square meter divided by tons of CO2. So that's also tons of CO2. And then this one, you've got your time and your inverse time, because that's the rate, a rate there, 0.3% per year. So those cancel out, and everything has units of tons of CO2 inside the brackets. And then this coefficient is just the warming you get per ton of CO2. So the answer to David Dean's, whose question was it? Somebody asked about methane. Apologies, I haven't got they've disappeared up the screen. So methane is sort of in this driving other things driving global energy imbalance. That's in this term. So if we push up methane emissions, that causes a lot of global warming. That's happening at the moment. That's why the world is warming so fast right now. We can digress on why methane emissions are going up, but it probably does have something to do with the gas industry. I mean, what do you call natural gas in North America? Anyway, methane, you know what that is. Then there was another question about from Andrew Spriggs about why we didn't see warming in the middle part of the century, again, because when CO2 emissions were still going up, again, this was going up, but this was going down because of the aerosol interactions with clouds that Philip was describing in his opening remarks. So when you've got a balance between two terms in this equation, you can end up with no warming over a few decades. But in the end, it's the CO2 term that really accumulates and drives the long-term warming. So that's the one that ultimately matters. And lastly, Kotik Lee asked, what about non-linearity? Well, this is kind of the point here. This is a linear equation, and so far, it seems to describe human-induced warming remarkably well. But of course, it's a linear equation because these coefficients are approximately constant so far. If they were to change, then that would be a non-linear transition, a non-linear climate change that could happen. And somebody asked the interesting question, can we be confident that non-linear surprises will be worse, will be positive or negative? I think broadly speaking, we can be pretty confident that a non-linear transition in the global climate system would be tough to live through. Because we're sort of used to a fairly benign climate, but of course there is a benign non-linearity, which would be a kind of a capping effect, which would mean that you don't you carry on adding a forcing, but for something limits the warming. But what that tends to be associated with is a kind of ratcheting effect as well. So you have a capping effect due to some phenomenon. And then it bursts through, and then you get a sudden amount of warming at the end of it. So broadly speaking, I think a linear response is probably the best we can hope for. That's my assessment, at least.
Great, thanks, Myles. So we'll pick up a question for Hannah, and that is by Chris Daniels. Do your digital twins work in real time or quicker than that? And there's an advantage if they were quicker than the real world.
So I can say a few things. So, I mean, one of there's a very big, exciting European Union project, which is planning to use these digital twin Earths. And so there, it's not so much a real-time kind of forecast that is wanted there. I mean, we will be pulling in real-time observations to ensure that the kind of model is as close to the current state of the system as possible, but then we can perform these experiments, not necessarily needing the information in real time. However, I suppose I should say that, I mean, if you're talking about real-time forecast and this kind of resolution, then I mean, what you're talking about is a weather forecast. And so so these are forecasts that we can produce in real time and at these kind of resolutions on a global scale. I don't know if that answered the question.
I think that was pretty much spot on. So it's perfect. Then there was a question about adaptive meshes. Would adaptive meshes be helpful so that you can ignore boring areas? That's a question by William Gallifand.
Yeah, so adaptive meshes, I mean, some people are considering them. So there are some kind of difficulties which arise with them. So one of the difficulties then is that the way the model is designed is it has these kind of subgrid representation, so things like clouds and kind of convective storms. And so then you're requiring the subgrid representation that you've developed to work equally well at all pixel sizes. And so that's quite difficult if in some regions of your atmosphere, you've got a kind of a massive grid box of 100 kilometers or something, and then in another region, you've got one that's much smaller. So that's quite difficult. So one place that is used more is in ocean modeling, but then they're not dynamic adaptive meshes, but kind of fixed adaptive meshes. And that's because you know where the small scale interesting features are occurring in the ocean, kind of along the boundary currents and so on. So that's a nice way to use it.
Great, thank you. So we've received many more questions than we can possibly answer, but I'll just maybe pose one last one that nicely might wrap up this session. It's by John Parker. Putting the two talks together, do you think digital twin ultra high resolution models will be used in climate attribution lawsuits?
Do you want to go first, Hannah?
I don't know, Myles, do you have a thought?
I can see it coming because at the end of the day, if you're blaming somebody for climate change, you're talking about, you have to talk about what the world would have been like without climate change, because kind of that's, you need that counterfactual. And to accurately understand a world without climate change, because we've changed the climate, we can only observe the climate we've got. We have no alternative but to use these digital twins to actually look at, you know, what would have happened if this and such had not occurred, if these greenhouse gases hadn't been dumped into the atmosphere, causing global warming. So I think it's coming, and you know, and in fact, one of the things I often argue is that I really look forward to the day when attribution, so this whole isn't something that this whole process of sort of assessing the role of climate change in extreme weather events is no longer something that people in universities do on a sort of ad hoc basis, but is actually part of the routine of weather forecasting services. And we are making progress on this. And Antje Weisheimer, who's another colleague here in Oxford, who actually works half her time at the European Centre for Medium Range Weather Forecasting, she's quite heavily involved along with Freddie Otto in the Environmental Change Institute in the development of Copernicus Climate Services. And part of that's the European Climate Services Initiative. And part of that is to address for the first time the attribution question. So, you know, I'm hoping one day at least the job of the weather, the job of the weathermen, so to speak, won't be the weather, and women, of course, the weather people won't be just to predict the weather, but also to explain it as well. And I think we need to get to that point, because we need this kind of information to become routine, so that you know, in decisions like the assignation of blame for individual events, the information's all out there and people are accustomed to it and people can make use of it.
Fantastic. Well, thank you so much to Hannah and Myles for two truly fascinating talks. Thanks to everyone for attending. It's not the same as meeting everyone in person at an alumni event, but it is, on the other hand, reaching a lot of people far away. So it's fantastic to have everyone there. So thank you very much. And if you have further questions, I'm sure colleagues don't mind to also respond to emails. I, for myself, don't mind at all. Please feel free to email if you have questions following up from these talks, and we're quite happy to answer these questions. So with that, thank you very much to everyone, and goodbye, good evening, or good morning, or whatever it is in your time zone for now.